Let me show you the Canvas page. And this, I need to stop sharing this one. So if I take the student view, yeah, so sorry for that. I updated this message a bit late yesterday, but I will try to put these materials a bit in advance, like 1 week in advance would be perfect, but I will try my best here. Here I put the Zoom meeting on this announcement, but later on I plan to put all the Zoom meetings on the syllabus. So you will find the link here. So we will have a new Zoom meeting for the tutorial starting at 12:15. And now if we look at how the course is organized. So this first introduction here is about literature and lecture plan and literature. And there was a question now. Yes, as you noticed, you have 4 different literature. I would say that actually the main source that we are going to use is number 3 here, Arnefoss. And this is, unfortunately, it has not been published in the form of a book, but you can easily find it on internet. So you can download the PDF based on this title here from 2015. And that's a very good literature. It's also one that we use for PhD course later on. Number 4 is, it was what was used mostly for the bachelor course with a steady state operation. Yeah, and also number 2. So, but as you see here, we will use reference 2 and 4 for the module 1. 2, 4, 2, 4, 2, 4. And then on, also a bit on number 4 on module 2, which is about power electronic converters. And then it will be mostly number 3. And the last lecture is, well, literature number 1 is more about, if you don't like too much equations, then you can read literature 1, which is more explanation and much less equations. It's more written for engineers than for students, I would say. And let's look at the general info. So these are the 2 time slots we have. About assessment, yes. So we have 9 tutorials. And what I do is that, okay, I can show you this on Canvas. If you go to the home. Now I only have a module 1, but it will be module 2, 3, and 4. And to unlock module 2, you will have to answer this task in module 1. So once you have view lecture 1 and got at least 2 out of 5 points in problem 1, 2 out of 4 in problem 2, this is not mandatory. and 2 out of 4 points in problem 4, then it will unlock the next module and you will be able to follow the rest of the course. If for any reason you have some problems and you don't manage to unlock these problems here, just let me know and I will help you. But I will also help you anytime during the tutorials if you have questions, of course. And I already published material for previous exams, so it's nice if you can have a look at the previous exams when we are advanced in the course and see what exercise can be answered. Because exams from year to year are similar type. And the submission for this assignment here is done if you go to the assignment part here. If you want to submit the first problem, it will open here. It's based on MATLAB. So here you can enter your answer directly in a MATLAB language. And then you can run a script or you run pretest to see if you get correct. And that will test the results for you. So now it's not correct, it's red, red, red. And then, but if you get green, 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 you can submit it. Or you can submit it when you are satisfied with your results. Back to the PDF. It will be a digital exam. We don't have any choice here. And usually it's 3 hours a written exam, but it will be plus 1 hour to count for the digital problems. For example, if you have to upload the solutions and to if your computer is crashing or something. And this will account for 60% of the final grade, because 40% will be on a project. And here, yes, and the project will start after we are finished with 9 lectures. So the 9 first weeks. 9 first weeks will be only lectures and tutorials, and then the remaining will be project. So this is a literature I spoke about. Yes, I already told you, and here I put also all the chapters that are relevant. And here are the 4 modules. So this the first 3 weeks will be introduction that we did and mechanical requirement, and then this is a repetition of the bachelor course, but we need the basic principles to understand how it works. So lecture 2 and 3 will be some repetitions. Actually not, because the permanent magnet has not been seen in the bachelor course. And then module 2 about power electronic converter, PEC. And then module 3 will be on dynamic models. And module 4 on vector control and drive selection. So we don't have any break in between. So it's I think no, sorry, we have 1 break in April because it's Easter holidays. But otherwise, we won't have any winter holidays here. So it's every Thursday. Yeah. Okay, I have some questions on the chat, I see. Does problem 1.4 give points to the overall grade? Or 1.3? Yeah, the one that was not mandatory to submit. But actually, none of the program will give any point for the final grade. It's just to practice and to unlock the next modules. But it will not count for, even if you get A on all the tutorials, it will not count on the final grade. It's just an exam and the report for the project. But the program 1.3 is not needed to unlock the module 2. So if that was the question. Yes, it will be a group project. But in some cases, if you have good, you are also allowed to have to be one in the group now. Okay, that was for the question on the chat. Yes, so that was for the lecture 0. And now I will share again the PowerPoint and start the record again. It takes some time to, each time it's re-preparing the slides, so I shouldn't. Here it comes. I have to scroll down the whole thing. Because it's not a PowerPoint, it's this virtual background, that's why. So here we come. Sorry, I went too far. Yes. Just one moment, and I will start again. Okay, let's start. I start the recording now. So in this part, we will look at the mechanical system requirements, because we have to understand the type of loads that can be attached to an electrical machine, and some coupling mechanisms. And at the end, we will look at how to find the rating for a duty cycle, given a duty cycle. So we can have 3 types of load. And now I will try something, sorry for the interruption again. so now you should be able to see my writing screen. But it seems something is wrong. Okay, now we can see. So we have a different type of load. The first one is a constant torque. And this means that if we look at the graph on the speed, with n is a speed in RPM of the motor. If we look at the load torque, TL, which would be in Newton meter, then a constant torque application will require the constant load torque at any speed. So it will look like this. Now, if we look at the other one, which is a constant power, then we will have when the n times t is constant. So if we increase n, t will be inverse proportional to n. So it's a curve which looks like this. And then we have a squared torque application. And in this case, the torque will increase with the speed. And that's typically, it starts at zero speed, and then it's increased squared. It's typically the case for a blower or pump. So it's increasing with the square of the speed. Okay, back to the slideshow. If we now look at the ideal gearbox, And I will also take this on the pad because it's quite important to understand these formulas here. So if we just write a gearbox, it looks with two. I'm not good at drawing this, but you have a different number of teeth. And then we have different radius. So you have R1 and radius R2. And then you have two shafts, one coming in and one coming out. And if we add inertia, if we put on the left side a motor with inertia Gm, and here we have inertia of the load GL, then we have a gearbox ratio. I can call it IGB, which is equal to the ratio of radius 1, or the number of teeth in the first gear, but it's also the same as the radius divided by the radius on the second. And if we have some speed, I call it omega 1, and here, if I take in the same direction, omega 2, then this will have a minus sign, omega 2 divided by omega 1. So to find this relation you can think that the speed on the contacts between the two gears will be the same, and the speed expressed in terms of R1 is R1 omega 1 on the left, and it's R2 omega 2 on the right. Except that if omega 1 is turning positive way, omega 2 will be negative. So that's why we have a minus sign also. So that's the first relation, one. And then if we have an ideal, so this is always the case, but if we have in addition, we know that it's ideal. And now I need to put some torque. So I call TE the torque from stator to rotor. So it's a motor torque. And then I call the T1, which is in the same direction here. And T1 will be the torque from the rotor to the gearbox. And then we have T2. That's the torque from the gearbox to the load. Oh, I have 7 new messages. Okay, the gray color is not easy to see. I think it will be better on the print later on, but yeah, I will try to keep in black then. And then we can also have an external force applied to the load, which I call TL. So TL is a torque applied from external to load. So now I have defined this torque, and then it will be easy now to write the Newton law. But what we say when it's ideal gearbox, we say that we have basically T1 times omega 1. So the power transmitted from the motor to the gearbox is equal to the power transmitted from the gearbox to the load. So T2 omega 2. So which means that T1 is equal to omega 2 divided by omega 1 times T2. And that's equal to minus the gearbox ratio times T2. So that's this one here that we should. So that will be equation 2. And now let's write the Newton's law for the gear 1 and then for the gear 2. So the gear 1 has inertia Jm and the gear 2 has inertia Jl. Then I will have J1 derivative of omega 1 dt equal okay, there is some bug because it should go to the next page now. I have to fix this and I will be back. Okay. G1 d omega 1 over dt, that will be the torque applied by the motor, TE, minus T1. So minus or plus the torque from the gearbox to the rotor, which is equal to minus the torque from the rotor to the gearbox. So it's minus T1 here. That's my equation 3. And then I do the same with, and G1 is actually Gm. And then we have GL times d omega 2 divided by dt. That will be equal to external torque onto the load, TL. And then gearbox torque onto the load, T2. So plus T2 here. So now if I use equation 2 into equation 3, then I can rewrite this one, Gm d omega 1 divided by dt equal to Te minus, and T1 was equal to omega 2 divided by omega 1 T2. And that's my equation 5. And now if we use equation 4, then I can use T2 as a function of TL and GL. Then I got G1 or Gm d omega 1 dt. That's equal to Te minus omega 2 divided by omega 1 times T2, which is equal to GL d omega 2 divided by dt minus TL. And since we have omega 2 equal to it's equal to omega 2 divided by omega 1 times omega 1. Yeah. Then we can write Te. That's equal to the first term here, G1 or Gm. And if we look at this, d omega 2 divided by dt, that's the same as omega 2 divided by omega 1 times d omega 1 over dt. So we can factorize by d omega 1 divided by dt and multiply this and then put it on the other side. So that will be plus omega 2 divided by omega 1 square GL times d omega 1 dt. And then we have minus here omega 2 divided by omega 1 TL. If we look at gearbox ratio, we can also write Te equal to Gm plus IGB squared. No, sorry, I actually want to write it with R1, R2. IGB was equal to R1 divided by R2 squared GL. And this is what we call the equivalent inertia seen from the motor side. Or GH maybe, times d omega 1 dt yeah, minus omega 2 divided by omega 1 TL. I keep this because you will see when we have a several gearbox, it will be easier to use. So that's my formula for a gearbox and for the ideal gearbox. I don't know why I cannot turn pages. So we have GX equal to GM plus destination radius, which is R1. So we move the load inertia from the load side to the motor side. And the motor side is the side 1 and load is side 2. So it's R1, which is the destination radius, divided by the source radius. And this has to be squared and times GL. So let's now take an example. And we are still in an ideal case. So I make this example a bit more complicated than just one stage. We have two-stage gearbox. So let's write this. We have a GM, and then we have one gearbox with R1 radius and another and R2 on the other gear. And then we have here R3 and R4. And then here we attach inertial load. And we also have a TL, external load torque. So that's GL. And here we apply also this TE from the motor. And we will have a theta M motor, theta 2, theta 3, or L for the load. So the question is, find TE as a function of d omega m dt and TL. And we will do it in two different ways. We have Philip who is raising his hand. Please ask a question if you have. Okay, it was solved. So then you can unraise your hand now. Let's see. So we can say that we can consider this gearbox as these two stages as one gearbox with gear ratio R1 divided by R2 times R3 divided by R4. But then so we use the formula, the previous formula, TE is equal to GX, so the equivalent inertia times d omega m dt. And then here we had minus omega L divided by omega M times TL. And what is omega L divided by omega M? And GX. So GX, we can find it easily. So that if we look at the motor side, it's GM plus, if we look at GM, we have a destination, which is R1. Well, if we move the first here, since we don't have any inertia on the axis 2, we have 0 times R1 divided by R2 squared, which is still 0. We multiply by 0. And then the third inertia, GL, will be multiplied by destination is R3 divided by R4, and then R1 divided by R2. So we can put it together, and it will be R1 times R3 divided by R2, R4 squared times GL. And if we look now at omega L divided by omega M, sorry, I have yes. So we see that omega M is turning in the opposite way as theta 2 because of the gear, and then theta L is in opposite way as theta 2, which means that omega L divided by omega M, because theta L is turning in the same direction as theta M, omega L divided by omega M is positive. So we have minus omega L divided by omega M. That's equal to minus R1 R3 divided by R2 R4. All of the radius are positive numbers, so we need a minus here. But if we now, instead of considering the motor shaft, we can consider the shaft in the middle, so the theta 2 shaft. So if we write referred to theta 2 shaft, then the external applied force to theta 2 is equal to 0. And then we write the equivalent inertia at the theta 2 shaft, which is Gm, and then the destination is R2 now, because we move Gm to theta 2. So it's R2 divided by R1 squared Gm. Zero on theta 2, and theta L, we have GL. Destination is R3 divided by R4 squared GL. So that's my equivalent inertia. And I multiply this by d omega 2 over dt. And then it's minus omega m divided by omega 2, which is because this omega theta m and theta 2 are turning in opposite sides, so the minus of omega divided by omega, it will be the plus. So it will be plus R2 divided by R1 TE. And the same for the other side, plus destination is R3 divided by R4 TL. And now if you consider that omega 2 is the same as omega 1 times R1 divided by R2, no, R2 divided by R1. Then we will come back to exactly the same formula as we had before. If I change the view option, I don't understand this. Then I could see the page. That's a comment on the chat. Oh yeah, can you take the page up there? Okay, yes. So as I said before, we add omega 2 is equal to minus omega 1 times R1 divided by R2. Okay, I have also a question here. Yes, if we take omega L divided by omega M, then we need to go backward. So it's R3 divided by R4 to get omega 2. And then it's R1 divided by R2 to get omega M. So then it becomes R1 times R3 divided by R2 divided by R4, yes. And I wrote something wrong then. I wrote R1, R3 divided by R2, R4. But you see that I wrote R1, R3 divided by R2, R3. This I cannot see. Yes, here, okay. Then it's a mistake, it's a 4 here. I have this problem with turning the pages. It works sometimes, but not. Just one moment, please. So we have omega 2 equal to minus R1 divided by R2 times omega 1. So we have the previous expression, which then becomes 0 equal to R2 divided by R1 squared GM plus R3 divided by R4 squared GL. And then it's equal to minus d omega 1 dt R1 R2. Plus R3 divided by R4 TL plus R2 divided by R1 TE. And now if we want to get TE, then we multiply by R1 divided by R2. So I move the rest on the right here. So we will have this is a minus sign, so it's R1 divided by R2 times R2 divided by R1 square GM plus R3 divided by R4 square GL d omega 1 dt minus R3 divided by R4 TL, and this is multiplied by R1 divided by R2. So then I get TE equal to, this goes, this disappears, it's GM plus R1 R3 divided by R2 R4 squared GL d omega 1 dt. And then here we have minus R1 R2 times R3 divided by R4. R1 R3 divided by R2 R4 TL, which is the same result as we had previously if we were moving the inertia on the motor shaft. Okay, I will stop sharing now. I stopped recording. We take also a 10 minutes break. And then we start next part, which will be non-ideal gearbox and then simulation. So let's start again at 5 to 11.